Recording is rolling. It's Monday, May 16th. Right, so a few announcements pop. Next couple of days, I've got some weird schedules going on. There's like some exams I got to proctor and some place I got to be. So here's what we're looking at. All right, so next couple of days, I'll be here. Well, kind of in the morning, but not necessarily by the time I get to the end of the day. But that'd be all right because I will set you guys up with paper roller coaster what we're doing. So today we're going to finish this quantum mechanics journal, right? And then I'll set you guys up with paper roller coaster. You guys see on your desk some foam boards and some paper roller coaster templates, right? So yeah, that'll be pretty much from here on out. I have a couple other things going, but gonna be mainly what we're doing from here on out. Right. Let's look at senior final exam schedule. So period 4, you guys did already. Today it's 1st and 7th. Right. And then if you're a senior, well, next couple of days for your other classes. Right now for everybody else, remember your exam is until where's it? Here we go. Monday the 23rd is the first one, that 7th period. All right, so just reminders, things going on around here. All right, let's hop into the quantum mechanics packet. Lasers. All right, so I do have a real short video on this one. I'll just cap as best I can, kind of like a minute physics. So that's how lasers work. Okay, there's quantum mechanics connection. So how does a laser work? Okay. I'm not sure 100% follow this explanation, but do my best. What I've been told, and we're gonna go with it. So here's like the body of the laser. Okay. Got lots of photons in here, right? Only you guys know that photons, well, they're not exactly dots like that, like particles. They're really more like waves, right? Wave packet. Okay. Okay. And if you can get these photons bounce back and forth between two mirrors, right? So I got mirror. Then on the other side mirror, okay, so you get them to bounce back and forth. Okay. Well, they're going to like interfere with each other. So if here's photon, got a bunch of photons, right? They're going to interfere with each other, maybe like constructively, destructively, right? I think, well, you know, maybe it's random. Sometimes they'll be in phase, sometimes not. Right. So what's the deal with like a bunch of coherent in phase light coming out the other end, which is what a laser is, right? Got this coherent in phase laser light, right? And it has something to do with there's this analogy with like flipping coins, right? So show you guys 4 scenarios, right? So suppose you had 2 coins and you flip 2 coins. So we'll go coin 1 and coin 2, right? You might have, oh yeah. Huh? What? Physics textbooks. Oh, yeah. Yes. All right. All right. So you might flip a coin, get heads and heads. You might flip a coin, you get tails and tails. You might get heads and tails, and then tails and heads, right? I mean, those would be the 4 possibilities, right? And I mean, in like classical physics or like everyday world, say, okay, well, each of these has about a 25% chance of happening, right? But in quantum mechanics, and you've got these photons that are actually waves that's hard to distinguish one from the other. Turns out that where they would have, say, like heads and heads or tails and tails, where like so the analogy is like they would be in phase. Okay. That's actually going to happen about 2/3 of the time. Okay. And for them to be out of phase, like the coins would be opposite, that's only going to happen about 1/3 of the time. Okay. The fact that they're more likely to be in phase, again, so quantum mechanics effect makes it possible to create this coherent in phase laser light. All right. So let's hang it from that. If you're curious about lasers and want to look more into that, then that is a concept that you can look up. That's one I'm going to handle myself too. Hawking radiation, right? So suppose you're out in the middle of deep space, like between the solar system and the next solar system. Like what's out there in the vacuum of space, right? They might say nothing, or you might say, well, okay, maybe there's like a couple of hydrogen atoms per cubic meter, just something like crazy spread out, right? But in quantum mechanics, in the vacuum of space, well, you can never have a pure true vacuum because particles and antiparticles will spontaneously appear and annihilate each other. Okay, now that's the setup for this. Now, when that happens, one particle, like the actual particle, has positive mass and positive energy, and the antiparticle has negative mass and negative energy. So I'll call this A for antiparticle and P for particle, right? And normally, okay, it's a wash. It makes no difference as if they were never there at all. So they spontaneously appear, but then they just annihilate each other. Okay, what's the big deal? But here's where this actually matters, is at the edge of a black hole. Suppose there's like a black hole right here. Okay. So I'll call this guy a black hole. Okay. Well, because the actual particle could have positive energy, but the antiparticle has negative energy, negative mass, negative energy, there's a greater likelihood that the antiparticle actually gets pulled into the black hole and the particle might actually escape out into the universe. Okay? So at the edge of black hole, the antiparticle is more likely to fall into the black hole, and the particle is more likely to escape out into the universe. Okay. And what that's going to do then, right? If this black hole is just absorbing this negative mass and negative energy, is this will eventually evaporate the black hole. Okay. Now, eventually, what is eventually? Eventually might be like 1 trillion years, where you guys know the age of the universe is only 14 billion years old. So this is like a crazy long time process for this to ever happen. Okay. But the particle that escapes out into the wider universe, this is what the Hawking radiation is. Hawking's radiation. Okay. And it can be detected, and it's there. This is all a quantum physics effect. Yeah, so black holes will literally evaporate, sizzle away. Actually, when they get small enough, supposedly they'll actually at some point explode and waste all their energy at once. It's small enough, so there you go. Right. Let's go back.
Obviously, like black. Became black.
Okay, radioactive decay and carbon-14 dating. Yeah, you know what I'm gonna do? Yeah, okay, yeah, let's do this. Okay. So this involves the weak nuclear force. Okay. So the weak nuclear force it's related to radioactive decay. Don't know much other than that. So I'm going off, so teach you guys. And not all atoms radioactive decay, but some do. So one example of something is that undergoes radioactive decay is carbon-14. Carbon-14, which has a half-life of about 5,730 years. Okay, you can see this by just watching it decay in a laboratory, right? So you just wait some time, go see it. Okay. So suppose you have like 10 grams of carbon-14, right? After 5,730 years, at that point, since that is the half-life, now you're down from 10 grams all the way down to 5 grams, right? Wait another 5,700 years, well, now you're down to 2.5 grams, right? Okay, so each individual atom, right? There's some probability that it will decay at any moment, but like in aggregate, you can watch this process happen. Right? Living organic matter has a certain concentration of carbon-14. So living organic matter has no concentration of carbon-14. Okay. But as soon as like some living being died, whether we're talking about like a plant or an animal, okay, then that carbon-14 will start to dissipate. Right? So as long as it's staying alive, that proportion is maintained. But as soon as it died, and you can actually use this to date organic material. Right? Like how long ago did this object die, and therefore the carbon-14 started to dissipate? I'll get you guys a graph for this. Okay, what would a graph look like? Okay. So look at like some amount of carbon-14, or this could really be anything that's radioactive, right? As a function of time, right? And here could be like time. So 0 seconds have passed, maybe something like in terms of carbon-14, maybe like something died just like this morning. Right? And so it's got this much carbon-14. Anything living should be expected to have that much. Right? After one half-life, so for carbon-14, this would be 5,730 years. So this might be T in years. Right? Well, there's some things have a half-life of like a fraction of a second, some are like tens of thousands of years. Right? So 5,730 years. Well, now we're down to half of the original amount. So this might be A naught, this would be half of A naught. Right? And then after another 5,730 years, so now we're up to like 11,000 something years, right? Well, now we're down to half of that, which is a quarter of the original, right? So wouldn't that go here? Okay. And couldn't you just do this process for like probably tens of thousands of years, right? Just right. That's an exponential decay, isn't it? So this is called exponential decay. Okay. And it's going to just horizontal asymptote of like 0 carbon-14. Okay. 4 fundamental forces. Right. So one of the first ones that one of the ones that we commonly use in here is like gravity, right? Gravitational force. Okay. And then there are considered to be 3 other fundamental forces. So I'm going to list these out. There's electromagnetism, which obviously anything to do with electricity or magnetism, but also like me just holding this pen, right? Because to get down to it, isn't just electrons pushing against electrons. Well, that's this one right here, right? And what are the other ones? So in this class, we only dealt with these 2, but the other 2 are the 2 nuclear forces, the strong and weak nuclear forces. So these are nuclear forces. Okay. Now, I left these 3 bottom ones as sort of separate from gravity, right? Why? Because these 3 right here, these 3 bottom ones, electromagnetism and the 2 nuclear forces, can be explained under the umbrella of the standard model. Standard model. You guys remember that from last week? Those like 17 elementary particles and the whole deal, right? But not gravity, which is kind of a problem because how do you have like some model of the universe that doesn't even incorporate gravity? So this is still an open question in physics. Could there be some larger theory that actually unifies all these forces? That's kind of where we're going with this next one. Okay. Now, I've seen a really good case made that gravity is actually not a force the way these other 3 are forces, but gravity is just an artifact of the warping of space-time by mass. So like when you feel gravity, it's, well, sort of explain this again. Einstein, this goes back to Einstein. Einstein said his happiest thought was imagining a man falling off the roof of a building. And the reason had to do with, as that man would be in free fall, right, ignore air drag for a moment, as that man was in free fall, his physics would be indistinguishable from being floating out in the middle of deep space, almost like a gravity field doesn't exist. Right? But he only feels a force when he like lands on the sidewalk below, and there's like a normal force pushing against him, right? So like all of us right now, he's like, yeah, I feel some weight, I feel some force, but what you're really experiencing is the normal force of like the ground pushing up against you. And Einstein's interpretation of this was that that is actually a force that's propelling you through space-time. Kind of like if you're on a merry-go-round, right, and you feel like you're being thrown to the outside, but we know there is no such thing as a centrifugal force. there's only the centripetal force that's pulling you in, holding you in a circle. But if you don't know that, it'd be kind of hard to tell, right? So from Einstein's point of view, what you might say is that these three bottom forces are sort of like the fabric of the universe, and then gravity is like the warping of that fabric. So, but physicists are still on the hunt for, is there some equation we can just pop everything into, so we can like do a bunch of numbers, variables, and figure out something that could incorporate all these, which then might give you some insight into what's going on inside black holes, what's going on, say, at the time of the Big Bang. Okay. So that's where we get to unification. Unification is the unifying of all four of these forces. Okay. And one of the only good proposals on the table goes back to the 1970s, something called string theory. Right. So here's the question: can gravity and quantum mechanics be unified into one theory? When I say gravity, I'm really talking about general relativity. Sometimes you hear it said that way. General relativity. Okay. Einstein physics, right? So there are, going back to the 1970s, there were these 5 perspectives on something called string theory, which involves vibrating strings on the order of magnitude of the Planck length, which is like crazy tiny, right? So whether you have like closed loops or like open-ended strings or whatever, right? So these different strings are going to correspond to like different atoms, and it involves like depending on how you count them, either 10 or 11 dimensions. So our brains can kind of understand 4, right? 3 spatial dimensions in time. So there's 4 dimensions, right? But then it could go up to, right? Now, if you bring these all together, so M theory is kind of a conglomeration of these 5 string theories. It's like, you realize, oh, actually, they're all like different math models pointing to the same thing. So this is ties together different perspectives of string theory. Problem is with this theory is like how to experimentally test. Right? Because a lot of good physics starts with like theoretical physics. Like somebody says, oh, we've got these math equations and got a little bit of knowledge and put it all together. On paper, this is the way this should work out, right? I mean, that's how Einstein uncovered relativity, right? He did a bunch of work on paper, and then people did a bunch of experiments like, oh yeah, like you're right, this theoretical physics is good, right? But problem with string theory is, I mean, it looks really nice on paper, the math works out really nice, but how do you test something that's like on the order of magnitude of a Planck length? So then at that point, if you can't test it, can it even fall into the realm of science? Because science, you want to be able to experiment. Right, what I want to mention about nanotechnology is here, go down this question. Could there be one day a molecular assembler where you could just create anything at the push of a button? Okay. So, for example, suppose you want to make a carrot cake, right? Well, we can make carrot cake now, right? Go to the store, get some flour, get some sugar, get some carrots, right? Mix it all together, put it in the oven, right? But if you want to get down to the like particle physics of it, you say, well, this is really made of like some proportion of some arrangement of like carbon and hydrogen and oxygen and phosphorus and right, all these elements. Could you ever just take those elements, right, themselves, and then just like pour them into a machine and hit a button, and you've got this molecular assembly? So, oh, here's how you put these together to make a carrot cake. I mean, I guess in principle, now you'd have to have definitely like mastered physics at that point. And we're talking about like moving little atoms around, right? Right. So yeah, you'd have to have mastered all this quantum mechanics and to be able to apply it in some kind of technology like this. I guess the one thing I would want to know too, besides just the ability to do something like this, is like, well, how energy intensive would this be? Would this require like an enormous amount of energy? Because then, if it runs into an energy problem, it's like, well, there might be like an economic limitation. Right? Unless, I don't know, maybe you could like create a whole Dyson sphere and just like beam these carrot cakes in space and send them down. But who knows? It's an interesting idea though. Possible future technology. Time will tell. All right, last few. Hey, let's do some calculations involving half-life. Right, so I've got two perspectives on half-life, and they're both going to converge and give you the same thing. Right, so one at a time. So one of them is this question: the amount of substance that you have. Right, so this is I should say final amount is equal to initial amount oh yeah yeah, we're good. All right. You guys could probably figure that out just having gone through this class. If you see the subscript not refers to as some initial amount, right? Okay, so we're going to take some initial amount, we're going to multiply by half some number of times, and that'll give us our final amount. Ooh, you guys see that's going to be like something to do with half-life, something to do with exponential decay, right? Because how many times are we going to multiply by half? Well, that's where this power comes into play, the superscript. So I got a fraction up here. So t is like time, like as a variable time, right? And t sub 1/2, that refers to half-life, which is unique to some particular substance, right? So for carbon-14, for example, the half-life is 5,700 some years. Okay, so if you count how much time has gone by, suppose 5,700 years have gone by. You take 5,700 divided by 5,700. See how that would be an exponent of 1? And do you see, therefore, how this whole fraction, t over t half, is telling you the number of half-lives that have passed? Right? It's giving you a count of the number of half-lives that the whole superscript is. Right? All right. And then if you know how many half-lives, like 1, 2, 3 half-lives, or it could be like 3.48, right? Then take 1/2 to that power. And that's the number of times that you're multiplying by half. Multiply that by your original amount, and that tells you how much you end up with, right? So let's do this piece by piece, because I got 4 perspectives on this, and this is eventually going to lead to like how you would actually use this as an archaeologist. But so one step at a time here. I got this table, whoops, got some numbers here. So half-life is 5,730 years. Hey, that's carbon-14, isn't it? C14 going on here. Let's say the amount that we start with is 256 grams. Right? Doesn't really make realistic sense, but let's run with it because the numbers are nice. Okay, complete this table. So I got time in years ticking by, and the amount. Well, we're gonna figure out. You know what? I should have thrown in a third column. I'm gonna throw this in right here. T. So I'll say a number of half-lives. Right now, if 0 years have gone by, doesn't it make sense that also 0 half-lives have gone by? So I'll put a 0 in this column. Okay. 5,730 years. Hey, doesn't that exactly correspond to 1 half-life for carbon-14? So that would be like 1 half-life. Right. Ooh, 11,000 some years. Isn't that like 2 half-life? Or whoops, yeah, 2 half-lives. Right. Oh, 17,000 years. That looks like the original amount times 3, so that's 3 half-lives. 22,000 years, that looks like 4 half-lives. 28,000 years, that looks like 5 half-lives, right? You guys see that? It's like a count, like I very conveniently chose numbers of passing years that correspond to integer number of half-lives. You guys see that? Right. So how much substance do we have left? Right. Well, let's see. If 0 years have gone by, right? 0 years. What is 0 divided by anything is 0? So superscript is 0. Guys, what is 1/2 to the power of 0? What is anything to the power of 0? And it's not 0, it's 1. So we're gonna take our original amount, just multiply by 1. Oh, and the original amount was 256, so we still got 256 grams. Okay, so if 0 years have gone by, we're gonna multiply by 1/2 0 times. That just means we still have the original amount, right? This is kind of one of the reasons that anything to the power of 0 is 1, right? Fits with an example like this. Now let's say 5,700 years have gone by. Hey, isn't that exactly 1 half-life? Right? Ooh, let's see what happens to the numbers. 5,700, 5,700, that's 1. 1/2 to the power 1 is half. It's only done that once. Half of 256. Isn't that like 128? Now we're down to 128 grams. Right? 11,000 years. If you plug in 11,000 over 5,700, that's 2. 1/2 to the power 2. So that's a half times a half. Isn't that like a quarter? Oh, so that's like a half done twice. Now we're down to 64 grams. See, like every single half-life that passes, we're gonna like half of it, what's remaining decays. We're down 32 grams, then 16 grams, then 8 grams, right? And this could just keep on going, right? Is that? Now, I should say, I mean, when you're hitting like the 30,000 year mark, since this is probabilistic, when we eventually get to the actual half-life application of this, and it's kind of hard to date anything like older than this because the numbers kind of fuzzy at that point. Is this really going to be 8 or is it going to be like 6.5 or 11.7? It's like, kind of probabilistic thing. Okay. You know, especially if you have a tiny concentration to work with. All right. Guys good so far? Okay, let's do the next quadrant. Now this is we got the same premise. Half-life still 5,730 years, right? But now I'm giving you guys a more like formal mathematical approach, right? That's going to involve. We're about to do some logarithms, right? You guys remember logarithms versus exponents, right? The opposite processes, right? The way we already did, the way we just did it so far is maybe the more intuitive way. We just multiply by half some number of times. Okay? Okay, so let's do this way. We're going to solve for k. Now k is some constant that has to do with half-life, but it's gonna be its own thing. Okay. Oh. Thank you. All right, so check this out. I'm going to plug in a scenario that involves exactly 1 half-life so that I can solve for k. And if that's true, then wouldn't the amount that we end up with be half of the original amount, regardless of what the original amount is? Okay. So times e to the negative kt, right? I should tell you guys, whatever version of this formula that you're using, it's referring to the exact same curve, and I can show you exactly what that curve looks like. That's this guy right here, isn't it? We already did this a few quadrants ago. You guys remember this one? So you start with some amount, and then you got this exponential decay curve that has a horizontal asymptote at the 0 mark. Right? Right. So you can choose any starting amount, and when you end up with half of that, that would correspond to 1 half-life. So I shouldn't even say t here. I should plug in 5,730 years. Right? Wouldn't that be true? A naught cancels. Right. Let's go solve for k. You guys ready to solve for k? Right. Oh, I forgot to tell you guys what e is. E is a very special number in mathematics. Actually, I bet some of you guys know it's an irrational number, kind of like pi. Like pi, you say, oh, 3.14159, blah, 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 right? E is kind of like that. Does anybody know what's E equal to? Yeah, 2.71828. And then again, it's irrational, so it goes on forever, no repeat. Oh, I can show you that here too on the calculator because the numbers are embedded into the calculator. See how there's a e to the x button. So I hit second e to the x and then type in 1. So e to the power 1, that would just be itself, right? Oh, 2.71828. Oh, look at that. Okay. And now, why is this number important, math? Because if you have e to the power of x, I mean, here's one application of this. The rate change of e to the x, which looks like this, just exponential growth instead of decay. Right? The rate change of that graph is the graph itself, and it's the only graph that does that. Right, so it's an interesting little pivot there. Right, so let's solve for k. Right, so I got 1/2 is equal to e to the power of negative k times 5,730. Expand this a little bit. Solve for k. Okay. Do you guys remember the next step? Maybe from a math class, you have to do what to both sides, take the. What you're trying to solve for is stuck in an exponent. How do you get it out of the exponent? You have to apply a logarithm, right? And in this case, we're going to use a special logarithm. There's actually 2 log buttons on your calculator. There's log base 10, because we use a base 10 system, but there's also natural log, ln natural log, which is log base e, which is this guy right here. Right? So I'm going to take log base e, the natural log of both sides, and what's effectively going to do is just bring down this whole negative k times 5730. Should say 5730 years. There's a unit there, right? So if you remember log rules, like rolling the log, the whole thing, probably from math class, right? It gets what used to be in the exponent is no longer in the exponent. Okay, so then divide both sides by 5730. K is equal to let's say this 2. Natural log of a half. Natural log of anything between 0 and 1 is going to be negative itself. Here, I'll prove it to you guys. Natural log of 0.5 is, see, it's a negative number, right? So if I really wanted to, I could scratch out both negatives, but I could call this ln of 2. Let's watch this. You guys see 0.693? What is natural log of 2? It's also 0.693, but it's positive this time, right? So if you like, you can throw in a little middle step here. You could say natural log of positive 2 is equal to positive k times 5730. You don't have to, but you could. Okay? Anyway, one way or another, k comes out to be natural log of 2 divided by 5730. Some version of that. Okay. All right, let's see what number that is. What is natural log of 2 all divided by 5730? Okay. That is 1.21 times 10 to the negative 4. Okay. Oh, I forgot this has units, years. Or I should say 1 over years. All right, so there you go. There's the solution. All right, really tiny number. Right. Now remember, this only applies to carbon-14 specifically. That's what the K value is. Okay. Now we're going to go solve exponential decay again using this more formal math formula. Okay. So, right, we've got half-life is what it was before. The original amount is exactly what it was before. Right. Solve for A at 22,900 years. Okay. Oh, well, don't we already have the answer to this question? Right? Which is right here. Shouldn't just the answer just be 16 grams? Okay. So the whole purpose of setting this up is to show you guys that this more formal math way of doing it is going to lead to something that you could figure out intuitively. The first way, just divide by 2 and keep it in, right? So let's try it out. What is 256 grams multiplied by e to the power of, say, negative kt, right? So it'd be negative natural log 2 over 5730 years times 22,920 years. Right? Right? Just plug it in. Oh, let's see what that gives us. What's 256 times e to the power of negative natural log of 2 over 5730 times 22,920. Okay. Now, when I hit enter, I already know what's going to pop up on my screen. Let's see if you guys are following. What's the answer to this calculation? 16. Yeah, 16 grams, because we already did it. Okay. Let's see. It is 16. Look at there. Look at there. So 16 grams. All right, so it works out. Okay, so we had to at least do one trial run to make sure that this stuff does work and match up with this. Okay, and it does. Okay, great. So we got that. Okay, you guys ready for the last one? The last one, we're going to close out this whole quantum journal. Okay. Now, what we've done so far, like these 3 quadrants, is you've been given how much time has passed and asked, well, how much substance do we have left, right? But the real world application, if you're an archaeologist, isn't it the exact opposite process? You pull some artifact out of the ground, you're like, I wonder how many years have passed, say like sulfur tea, since this organic material died back in the day. Yeah. Whether it's like some like animal bone that would be organic, or if it's like some paper, right, that probably hit from a tree at some point or some plant. Okay. Right. So then you can measure the concentration of carbon-14. Right. And then put it on this curve, right? So instead of knowing the time and figuring out how much amount there is, which is the last few calculations you did, you would be able to measure how much carbon-14 there is, and the less there is, the more time has gone by, right? Is that? And that's what we're about to do right here. So what do we got? We got half-life for carbon-14, 5730 years. Okay. Let's say the original concentration was like this number, 10 microgram per cubic meter, in some organic material for like some, something. Suppose you dig up some old artifact, it should be this number if it was living, but you only get 3 microgram per cubic meter. See, it's like less than a third. Huh. I wonder how old this this material is. Right? So we're gonna solve for T. So I have A, which is 3 microgram per cubic meter, is equal to A naught, which was 10 microgram per cubic meter, times e to the negative, now K, we got that up here, natural log of 2 over 5730 times T, and this time we're solving for T. Okay, you guys got that? Okay, so I'll walk you guys through the algebra steps. It's going to involve a natural log at some point. Before I do though, let's make a guess before we even start this thing. How old is this thing? Because here's what I'm thinking. What if you had 5 microgram per cubic meter? What if it was 5 and it should have been 10? Wouldn't that be exactly 1 half-life? So at that point, we would know it was 5730 years old, right? So the fact that there's even less than 5, well, that means it must be older than that, right? If it was 2.5, we would know exactly 2 half-lives. Like it's kind of getting close to 2.5, isn't it? That 3 is. So 2 half-lives would be about 11,000 years. I think this is probably going to be about 9 or 10,000 years old. Just looking at the numbers, right? You guys think that? Okay. Well, let's see if that's the case, right? So divide both sides by 10, and also the unit cancels. So 3 over 10 is equal to e to the negative ln2 over 5730. All times T, we're solving for T. This is all crazy power up here, right? Okay. Now we need to get this out of the power, I should say, like to the power up, right? And the only way to do that is a logarithm. So I'm going to use natural log because I've got E here. So I need natural log of 3 over 10 is equal to, okay, now the power is gone. Negative natural log of 2 over 5730. There's no more exponents. All times T. So T would equal, now pause for a moment. You might think, well, hold on, isn't one side negative, and so isn't it going to make negative sign? No, because natural log of 3 over 10 itself is a negative number, so all the negatives are going to cancel. That's going to be okay. Here's what it looks like all crazy. Got 5730 times natural log of 3/10 all over natural log of 2. Slap a negative sign in there, which is going to cancel out, and I should get a positive number. Okay, and hopefully that positive number is about 9 or 10,000 years. That's kind of what I'm looking for. Just that's an estimate. 5730 natural log of 3/10 all divided by negative natural log 2. Come on, a big positive number in thousands. Let's see. It is 9953 years. T is 9953 years. Right now that. Right now, realistically, that's a bit precise. Probably the best you could do is say that's about 9.9 to, wait, hold on. See if I count this right. But no, I should say 99 to 100 centuries old. Woo! That's some old artifact going on there. You guys got that? All right, so as we do, if you feel good about your whole quantum journal, like, okay, I got everything good to go. You can pop that in the grade tray and I will get you guys points. If you missed anything, then remember everything's on Google Classroom, so you can go find what you missed. If you were a senior testing one day, then you can miss just the ones that you missed that particular day, and I won't hold that against you because I know you were testing, and we're not going to turn this into a homework assignment. Right? Yeah. Go back to which one? To it. I will hand you the packet, and I'm going to get everybody else started on paper roller coasters. There you go. All right. Okay, so let me switch over and show you guys some paper roller coasters.